Welcome. Good morning. Today we discuss model adequacy test for multivariate linear regression. Under this we discuss some squares cross product matrices, then model adequacy test with Wills lambda.
We will continue multivariate linear regression, and now we will discuss about model adequacy test for multivariate linear regression, the model adequacy test. If you recollect multiple linear regression, so we have considered R square, RA square. We have also developed one table called ANOVA table for F test, correct? And what we have done, basically we have set certain hypothesis. That hypothesis is beta j equal to 0 for all j equal to 1 to p, and we created alternate hypothesis that beta j not equal to 0 for at least 1 xj. That was the hypothesis we have tested, and we have used this ANOVA table like this. Okay. In addition, what we have done also, while preparing the ANOVA table, we have found out that the total sum square or sum square total we divided or partitioned into two half, that is SSR plus SSE. That means the total or sum square total equal to sum square regressions then sum square residuals or sum square errors, correct. And using this, then degree of freedom was n minus 1, then here p plus n minus p minus 1. Okay. So, this one, in addition to this is basically all our model fitting. Coming to model fitting, in addition to this we have test of assumptions. That means we have done normality test, equal variance test, linearity test. We have also tested for autocorrelated errors, autocorrelation test. You can remember this. In addition, we also have done something called model diagnostics. That is basically coming under residual plots. And in multiple regression you find out that several residuals, different types of residuals, like your student age residuals, praise residuals or deleted residuals, then there was standardized residual, then we have seen that ultimately Cook's distance, then your d fits, d betas, so many things are there which are for finding out the leverage points, outliers, leverage points as well as outliers. Ultimately we say these are all influential observations. So, can all those things not be done in MVLR? You are getting me? It is possible, and most of the times the software will give you the outputs. Suppose SPSS, Minitab, SAS, CStat, Statistica, whatever software you use, ultimately you will get these outputs. Okay. So, we will see some analog from MLR to MVLR, that means multivariate linear regression. And if you do little more imagination, then what you will find out that it is just MLR if it is related to ANOVA, then MLR is similar to MANOVA. Getting me? So, now let us see that in MVLR how do we get that F test, R square, R square, similar thing, and how do we partition the matrix? That matrix is that total sum square cross product matrix, all those things. And what about the test of error assumptions? This is the in totality we will be discussing within this 1 hour or 50 minutes of time. Okay. So, then let us write down again in the last class what we have written, and so that you can correlate with this. We say this is n cross q, where n is the number of observations, q is the number of dependent variables, then we say this one is our n cross p plus 1. So, our p is number of IVs and your beta is your p plus 1 cross q. Okay. So, now what is q? Q is number of DVs, then this one is n cross q. Okay. So, this equation will be using, and once you have estimate that y cap, this is your x beta cap, and also we know that epsilon cap is y minus y cap. These are the few things we have discussed earlier, and these things will be required. So, what we will do with these things? Suppose I want to know y transpose y. Getting me? I want to know y transpose y. What will be this? This will be x beta plus this transpose into x beta this, because we are writing same equation, that this transpose this into this. Okay. Now, if I write y cap transpose y cap, then this is nothing but x beta cap transpose x beta cap. Similarly, I can write this transpose epsilon cap, which is nothing but y minus y cap transpose y minus y cap. Okay. Now, I want to know what is this y transpose y. What is y? Y is n cross q. Then what is your transpose? Q cross n. Correct? Then this one, if I write like this, some matrix you will be getting which is q cross q. Similarly, here you see this is again q cross n, n cross q. You will also be getting some matrix here of q cross q. Here this one is also q cross n, n cross q. You will be getting something here q cross q. So, if I say this is my SSCP total, which is a q cross q matrix, this is my SSCP y cap, that is basically what is the that regression point of view, how much we are getting. This is also equivalent. If I say this one is like this epsilon, if I write like this, or cap. Okay. So, you will find out in MLR what we have found out. We found out SST equal to SSR plus SSE. Similarly, here we can write like this: SSCP total equal to SSCP your y cap plus SSCP epsilon cap. Can you find any relationship with this with MANOVA? In MANOVA we have found out that SSCP total equal to SSCP between plus SSCP error within. In MANOVA we have used suppose T SSCP total equal to error between SSCP between plus SSCP error. So, because of q y variables your now matrix becomes like this. Suppose I want to create R square. Can I create R square here in the same manner here? R square is what? SSR by SST, that is from MLR point of view. But you will not get here because these are all in the matrix domain. But in MANOVA what we have done, we created one Wilks lambda, that one we say what is SSCP I think E divided by SSCP total. So, this is what is the likelihood ratio test. Now, can we get similar measure here in your multivariate linear regression case or not? Okay. So, yes, here in multivariate linear regression also we will go for likelihood ratio test, and here that R square like measures just exactly 1 to 1, that type of relationship is not possible. But yes, there are some other measures which basically were derived based on that F ratio, F statistics point of view, that what is this MSR by MSE. In R square ANOVA table you found out that F equal to MSR by MSE. So, MSR minus F MSE, this equal to 0. So, this type of relationship can be used and we will find out some measures with respect to this. Okay. So, in this context let me show you this slide. In this slide you see this for Y1, that is profit, this is for sales, these are residuals, getting me, residuals. So, how many y variable, 2 y variable. So, what will be the q cross q, 2 cross 2. So, this data can be used because this is epsilon cap. This data can be used to find out this 2 cross 2 that is SSCP matrix. Now, what is this one? This is the predicted one, which is y cap. So, predicted one, this predicted one when subtracted from the actual y value you have got this residual. So, this can be used to find out this SSCP y. Now, SSCP y will be SSCP y cap plus SSCP epsilon cap. So, repeat this fitted values will be used to find out SSCP y cap. This will be used to find out SSCP cap, and already y values are there, but you can check also using this formulation. Okay. So, in this example our Q is to show all SSCP total, that will be 2 cross 2 equal to SSCP y cap, that will be 2 cross 2 plus SSCP epsilon cap, that will be 2 cross 2. So, it is similar to your SST equal to SSR plus SSE. Okay. So, difference is this is the matrix domain, scalar. Okay, vector and scalar domain, basically matrix. Okay, fine. We will do some tests. The test is basically that what I can say here, a general test, that is what I can say, that generalized hypothesis testing. Generalized hypothesis, in the sense you have X data matrix, and which is basically your P plus 1 n cross P plus 1. So, your beta is there, this vector beta vector, which is how many beta is P plus 1 cross Q, correct, and your y variable. So, if I go by variable only, so if I go by variable, y is having Q cross 1 variable, x is having your, including the constant, I can say P plus 1 cross 1 variable, including constant is there. Okay. Now, you may be, so if I write down here for the y variable, Q1 variable case, so the beta part I can write like this: beta is beta 0, beta 1, beta 2, beta q. Will write? No, we will write like this: beta 1 to beta q. Okay. Now, this beta 0 contains P plus 1 into 1, this also contain beta 2 also contain P plus 1 cross 1, like this. Okay. So, this, that is why it is P plus 1 cross q. Fine. Now, what I will do here, I will say that sum of the variables, independent variables, are not contributing. Instead of writing that the jth variable is not contributing, I am saying, or we are trying to find out that sum of that independent variables are not contributing. Getting me? Subset of P plus P variables, constant knowledge is there, subset of P variables are not contributing towards explaining the y variability. So, here you have P plus 1, P plus 1, P plus 1. If I say that this one is starting from this, that is P plus 1 minus m up to this, then this one is m, because total is P plus 1. So, we are trying to say that this P plus 1 minus m, this many variables are contributing, and then remaining m variables are not contributing. Instead of writing that the particular beta k variable is not contributing, or beta j variable is not contributing, what you are doing here? You are simply saying that a subset of variable is not contributing. Getting me? If this is the case, so what I am then trying to say? I am trying to say that I am creating two sets. This one is your x0, this one we are writing like x within bracket m. Getting me? So that means I have total p plus 1 including constant p plus 1. So under H0, that is the null hypothesis H0, what we are saying that beta m, getting me? We are basically trying to say beta m which is equal to your that beta, this one is p plus 1 minus m. So that means p plus 1 minus m plus 1. So p minus m to beta p. I have beta 0 to beta p. I am taking the last m not contributing. So that means p to p minus m. So this is 0. This is 0. So please understand what we are trying to say. We are trying to say there are p variables, let it be 20, p equal to 20. So I am saying that that 15 variables are contributing, 5 variables as a whole they are not contributing. So I can rearrange those variables, first 15 variable contributing like this, p plus 1 minus m, that x0, and last is not contributing xm. We can write like this. So here also we are writing x0 within bracket, so that it will not be confused with x0, that constant, correct. Then H1 is here, that beta m not equal to 0 for at least one of the variable, for at least one beta mj. Okay. That means the remaining the variables what you are discarding, they are not to be discarded, they are also contributing. Okay. So then under such situation, if I want to write down what is the expected value of y, this is nothing but expected value of x beta plus epsilon, which is nothing but expected value of x beta. The reason is expected value of epsilon, that is basically 0, and ultimately this lead to x beta only. Okay. So if you write this one like this, that x0 then xm, x0 and xm, x0 p plus 1, what is this? This one is n into p plus 1 minus m, and this one is n into m. Clear? So then same thing I can write for beta, beta 0, beta m. And what is this beta 0? This is definitely p plus 1 minus m cross q, and this one is your only that how many m cross q. The resultant will be basically this will be m cross q and this cross q, like this. Okay. So you can write down like this one, x0 beta 0 plus xm beta m. We are not considering the error term because we have taken expected value of this. If m variables are not contributing towards explaining the y's variability, so that ultimately what will happen, beta m will 0. So that means this resultant will be 0. Getting me? Your xm beta m is basically beta p minus m beta p minus m plus 1 like this, beta p, everything is 0. Whatever when you multiplied this into x p minus m, x p minus m plus 1 and x p, this resultant quantity also will become 0. So, what I am saying here, that this quantity 0 means this expected value is dependent on this. We are using 0 to denote that under H0 this is the situation. Then under H0 our value will be, y will be x0 beta 0 plus epsilon. So, I can write like epsilon 0. See, this is under H0. If we say that beta m is contributing, then we will write the alternate one. Alternate is no, this beta m 0 you have considered, that is false, which is basically x beta plus epsilon, what you have taken earlier. Getting me? So, what will happen here, if I fit this model vis-a-vis this model, you will be finding out SSCP epsilon 0 estimate here, and here also you will be finding out SSCP epsilon cap, this estimate. Getting me? Now, if we, as given by Johnson and Wichern in this book, I have seen that. So, if I say this is nothing but that estimate of this, or you can straight away write 0, and this is nothing but this one estimate of this. Okay. This I have taken from Johnson and Wichern. You just check. So, what will happen then? One hand I have taken the total set of independent variables. In the other hand, what we have taken? We have said that H0 is true, that means m variables are not contributing. Getting me? If H0 is true, then the SSCP from the reduced model and SSCP from the full model will be same, the error term will be same. So, as a result, if I say under H1 this model is my full model, and under H0 what is this model is reduced model, my question is that the error SSCP error, that matrix, that will be more or less equal. So, now if we create a ratio which is determinant of that full model SSCPE vis-a-vis your reduced model SSCPE, getting me? So, this ratio will vary, will stay in between 0 to 1. Okay. So, when it will become 0? Suppose, obviously, when I am going for full model, that this one it should be less than equal to should be, because in the reduced model you have eliminated many variables, their contribution you are not considering, that will come to the error term only, SSCPE. So, obviously, this now what will happen if this value is sufficiently small, sufficiently lower, okay, much lower than this value, it will be close to 0. If both are equal, it will be close to. Okay. So, if you find what does it indicate? If you find out that lambda, that this lambda is known as Will's lambda, that in a MANOVA you have tested this, if this value is sufficiently close to 0, then what it is indicating? It is indicating that sigma, capital sigma cap 0 is much more than the full model sigma cap. Getting me? So, as a result you reject H0, but if it is equal to close to, it will not get 1. If it is close to 1, accept H0.